In this video, I'm going to discuss about some frequently asked questions on regression in technical interviews for analytics. The first question is, what are the basic assumptions in ordinary least square regression? So when you do an estimation, OLS estimation, what are the basic assumptions? Some of the most important assumptions in OLS are the following. The model that you are trying to specify should be linear in parameter. That means it should be y equal to beta naught plus beta 1 x. You cannot have beta naught square or beta naught 1 multiplied to beta naught beta 2. So you cannot have a non-linear term in your model, non-linear of the in terms of the parameters. If you can have x square or x cube, that's not an issue, but you cannot have beta 1 square. And then the second assumption is the residuals should be statistically independent, or the residuals should not be correlated. That means the covariance or the between your residuals like should not be a non-zero value. Okay, so the residuals should not be correlated. That means the data should be taken from or the sample data that you are using for estimation purpose should be completely random. It cannot be a biased sample. Then the next assumption is that the expected value of the residuals. So when we say expected value, we mean the mean of the residuals should be 0. So that's another important assumption. And then the residuals should have uniform variance. Else there will be the problem of heteroscedasticity, and your parameter estimates cannot be interpretable in a normal way. So ensure that the variance of the residuals should be uniform. And then the residuals should be normally distributed. So that's one of the assumption, although it's not a necessary most important assumption for estimation purpose. But if the residuals are normally distributed, then you will get the best set of estimates. That means the estimates are the best one. You can always estimate without even having normally distributed residuals, but your best results will come only when the errors are distributed normally. So these are some important assumption in OLS regression. What are the main differences between ordinary least square estimation and the maximum likelihood estimation? Well, we know that two popular estimation technique in multiple regressions are the OLS and the MLE. Now, how are they different? The OLS tries to find out the parameters by minimizing the sum of the residuals, right? So we define residuals like this. We define residuals like you have your say for example your dependent variable is y, and your estimated value of dependent variable is y hat. Then when you subtract, you actually get the residual, right, for each observation. And when you sum it and when you square it, just to ensure that it's a positive number, and just take a summation over all the observations, you actually get the sum of the square of the residuals, right? And you try to minimize this. So this is like a loss function. We want to ensure that the loss function is minimized. So for what value of your parameters your residuals is minimum. So that's what OLS does, and finds out your parameters betas, right? On the other hand, MLE doesn't use this technique. Well, MLE ensures that the values of the parameters, it finds out the values of the parameters by maximizing the log likelihood value, right? So it finds out the likelihood first, which is nothing but the joint distribution of the density function. For example, if your data is distributed normally with mu and sigma as the parameters, So it finds out the joint distribution for all your observations and finds out the logarithm, the likelihood, sorry. And likelihood is nothing but the product of all your density values for each one of these observations, and you take the log of your likelihood and minimize it using simple optimization technique, and finds out thereby find out the parameters, right, by equating it to 0, by equating the derivative to 0, and finds out the beta naught and beta 1. Sometimes it's not possible to do the minimizations by simply taking the derivative. So you do not have a closed form solution all the time. It's only possible in few probability distributions. So MLE is different in the sense that it doesn't use the least squares technique. So it's different, and sometimes you will and most of the times you will see that the log likelihood estimation or the MLE estimation converges towards the Euler's estimations, particularly in the case of multiple linear regression. So Euler's gives closed form solutions. That means you always get an exact solution for your optimization problem, whereas MLE doesn't give a closed form solution for all types of regressions. For example, in logistic regression, you cannot have a closed form solution. So you always have to find out the solution for this iteratively. That means for all observations will be used one after the other, and the likelihood estimates will be calculated, and the one which for a set of parameters for which the log likelihood value is the minimum is going to be used as the final parameters. So that's basically the way the maximum likelihood estimations is performed. The next question is what do you mean by biasness? And we often hear this term, and when do we say that a parameter is biased? Okay, this is often a question asked in interviews. Well, the biasness in any statistics which is computed or estimated is nothing but the difference between the expected value, or nothing but the mean of the estimation or estimated values from different samples of the parameters and the actual value of the parameters, right? So you have the expected values, you subtract the expected value and the actual values, the actual parameter which is estimated, and you will get the biasness, right? So and when do we say that a parameter is biased? Well, when you do an estimation, say for example you are doing an Euler's estimation, you first calculate your mean square error, right? So mean square is nothing but you take the difference in the actual values and the estimated values, square it and sum it across, you'll get your mean square error, right? So which is a combination of your variance of beta and the biasness of beta, right? You compute your beta values, so you will have one aspect to it, which is actual variance. It changes with your sample, and there is something called biasness. It depends on the estimator. So the estimator could not be or may not be the suitable one. It can give some biased value. It can overfit your data and can give a less it either underestimates or overestimate your beta values, right? And there is a variance of beta which is quite obvious if you keep on changing your samples, whereas a bias is something that something that we expect it to be 0, and we call it as unbiased, but sometimes it's biased. But the sampling variance is something that is unavoidable because it keeps on changing with your change in samples, the sample that you have taken for estimation. So something that is unavoidable, but we cannot avoid that. But bias is something that can well be avoided. Sometimes bias helps for better prediction. So regressions like lasso regression are specifically used, which uses some sort of biasness to ensure that the prediction or the predictive power of the model is actually increased. The next question is, what is standard error, and when do you get biased standard errors? Well, standard error is nothing but the standard deviation of the distribution of estimated parameters. So when you when you find out the parameters by estimating, you will see that the parameters like beta naught, beta 1, beta 2, these parameters will keep on changing with respect to the samples used, right? So you will get different values, and the standard deviation of the different values that you get for all these parameters has been given, or in general is known in a different terminology is given to it. We call it as standard error. So it's some sort of a standard deviation of these values and just known as standard error. And we expect the standard error to be accurate enough. It should not be underestimated, should not be overestimated. We call bias standard error, which means that it's either underestimated or overestimated. So that will give not so good results if it's either underestimated. That means we are some sort of we were saying that it's going to be accurate enough, which is not true, or we are saying that it's going to be totally vague. It's totally unpredictable. That's also not a good sign of a good model. And you get the standard error is biased, or something that totally different from what is expected when there are like too many outliers in your data sets. The next question is, what is the multicollinearity, and why is it an issue? Well, the multicollinearity is a problem that is faced in multiple regressions when you have more than one independent variables in your model. When the independent variables in multiple regressions are highly correlated, then you face an issue known as multicollinearity. Or in other words, if one of the variable in a regression model is a combination of two or more variables, more independent variables, then we call that problem as multicollinearity. It's going to be difficult for to have a good model with multicollinearity. So it affects or it violates an assumption known as the ceteris paribus assumptions. So what does it say? Let's assume there is a model y is equal to beta naught plus beta 1 x1 plus beta 2 x2. So there are two independent variables x1 and x2, and they are highly correlated. So we call that situation as multicollinearity, right? So when we have finalized our model, we always try to find out what is the marginal impact of one variable on the other, right? So if we have finalized this model, we want to know that if we increase x1 by 1 unit, what will be the corresponding impact on y, right? So we want to find out what is delta y by delta x1, right? And we assume that given x2 is constant, right, we increase x1, we keep x2 constant, and we increase x1, and we try to find out what is the corresponding change in y, and that's what we call as marginal impact, or the change in x1 has an impact on y, right? Similarly, when we want to measure the impact of change in x2 on y, we keep x1 as constant, right? So this particular way of finding out the impact of one variable on the dependent variable by keeping the other variables constant is known as the ceteris paribus. So when these two variables are correlated, say x1 and x2 are correlated, you cannot say that you can keep x1 constant and then increase x2, because they are correlated. If you increase x2, x1 is definitely going to change, right? Either if it's negatively correlated, it's going to go down. If it is positively correlated, it's going to go up. So they are going to be very they will be moving together or moving in opposite direction when they are highly correlated. Minor correlation, small correlation is okay, it doesn't have much of an impact, but anything significant is going to be problematic. So the problem of multicollinearity increases the variance of the parameters, right, and making them very unstable, right. A slight change in the sample, you change your sample, you use your data in a test data set. As you know that in any model we start with a training data set, and we also use a test or validation data set. So if you have high correlation or the problem multicollinearity, it's going to work well in training data set, will give you a good prediction, but it's not going to work in a test data set properly. Okay, and the so these are the two issues that we are going to face. It violates ceteris paribus, and it also gives wrong prediction sometimes in the out of sample data, right. So the next question is, how do we detect multicollinearity in the model data, and how do we take decisions on multicollinearity, how to remove multicollinearity? Firstly, we check the correlation matrix. So we should ensure that there should not be high correlation. Now it's a difficult thing to ask that what is actually high correlation. Is it 0.4? Is it 0.5? Is it 0.7? Well, there's nothing really which says that it's a high correlation. It depends on so many things. Sometimes 0.5 could be a high correlation, and sometimes 0.7 may not be a very high correlation thing. But usually anything above 0.4, 0.5 is considered to be highly correlated value. And if you have enough number of variables in a model, you should ensure that very highly correlated. There is no rule of thumb, there is no cutoff value as such, but normally the values which are presumed to be highly correlated or high correlation should be dropped from the model if you have enough variables. Otherwise you can always give and come up with solution to these problems, because you do not have too many variables, so you have no other option. The other way of finding out is using an index, which is an industry it's popular in industry, not in academics, but in popular in industry. So you find out the variance inflation factor, or shortly known as the VIF. So the VIF index tells you that how much variance of the estimates gets inflated because of the high collinearity, right. If it is under acceptable limit, then we don't really care, but if it goes beyond an acceptable limit, then it gives a warning, and we have to do something about it. So so BIF generally gives you that because of collinearity, how much the variance of your estimates like beta 1 beta naught is actually going up. We do not want a good variance, right. We want our standard error to be as minimum as possible, right. More standard error, more unstable are the parameters. We don't want that in the model, right. So when we get a VIF of 1, it's okay. Anything less than 5 is a small warning, you need to revisit, but still okay. Between 5 to 10, there is a strong warning that there is presence of multicollinearity and you should do something about it. And anything above 10 is completely unacceptable. So there is serious issue with the model when the VIF of a particular parameter is greater than 10, or that particular parameter is actually getting impacted, and you should do something about it. So you will get VIF for all the parameters in the model. If you have 5-6 parameters, you will get VIF for all these parameters after you have done the regression. So next question is, what are the remedies of the problem of multicollinearity? How do you ensure that this problem is handled properly? So the best way may not be the best way. In fact, it's one of the way. So we can't call it the best way, but one of the way to handle multicollinearity is to drop one of the correlated variable. Okay, If two variables are very correlated, highly correlated, you just try to drop one of the not so important variable, relatively less important variable. There are a number of ways of dropping it. It could be by using your common sense, just consult with the business or the stakeholders and see which one of these variables is more important, drop one of them. Or you can use statistical way of dropping variables. You can use stepwise regression. You can look at the significance value and see which one is having more significance. You can use more composite variable techniques like cluster analysis and finds out which variable is contributing more to the cluster or the principal component and use that particular value. Or the best way is which variable is actually more significant. Just check the p statistic or a chi-square statistics and finalize the variable. If there are two variables are correlated, the one which is having a better index, just keep that in the model, the other one just drop it. You can also use principal component. If it is a prediction model, just instead of using the raw variables, so the actual variables, use principal component analysis to come up with the principal component. And instead of using your variables, just use the principal component, which combines variable in some sort of way and takes care of your collinearity. Principal components are composite variables which are and there is it is ensured that the components are orthogonal to each other. That means they are uncorrelated to each other, right? So the multicollinearity problem is handled by using principal components in the regression. You can also use regression models which can handle multicollinearity properly. So one of the regression which is specifically used in dataset where variables are highly correlated is the partial least square or the PLS. So you can use PLS and avoid this problem. And multicollinearity is not a big problem if the model is for prediction purpose. So it's a predictive model. We're not bothered about the relationship of the dependent and independent variable. We don't want to interpret the relationship, the sign of the estimate, and the marginal impact of the independent variables on the dependent variable. We only care about the prediction. So multicollinearity is not a very big problem. In fact, it actually helps in prediction to a large extent. Of course, there is always limit to it. Beyond certain limit, it always creates problem. It creates issues. So that has to be taken into consideration. So thank you, and subscribe to this channel for more videos.